יש יותר סיכוי ש...
אני יודע סיבה. למה פיזיקאים פשוט בשביל לראות את האחר? אני כדאי חבות. חבות? יש לך חבות. או!
אתה צריך לעבור למקום הספציפי הזה במיוחד.
סטס, אפשר לזרוק על זה סולם רגע.
רגע. זה לא ככה. לאט לאט. turn it off? I will turn it off. לא, זה נורא, אי אפשר ככה. מה הבעיה בגלל זה? בוא נשרוף את זה. Okay, so I will all right, epilepsy by the end of the class. It's actually not funny. I have a friend whose son got an epilepsy attack just because of such a lamp. Yeah. But it's usually a genetical disease, so don't worry. If you have it. Go.
Wait, the guys home in the city.
There's problem. Alright, so where we stop? We are dealing with quantum gas. That's fine. Quantum gas. We consider an example where we have three levels. Epsilon 1, epsilon 2, and epsilon 3. What we managed to obtain that the partition function is factorizable, but it's factorizable not in terms of the particles. Right? I stopped caring about the particles. I'm doing everything with grand canonical ensemble. Grand canonical ensemble. I'm dealing with grand canonical ensemble, and I don't care, eventually, this is what factorization means, I absolutely don't care about, when I'm looking on a specific state, I don't care what happens at the other states. So the math led me to the following conclusion. I look on the partition function of each state, so for example Z1 is the partition function of state with epsilon 1. And I write it down as e to the power minus beta, the number of particles, ni, epsilon 1 minus mu, right? And I go ni, or this is n1, and n1 goes from 0 to 1. Because this state, this specific state, with energy epsilon 1, okay, can be occupied either by 0 particles or by one single particle. So Z1 is simply 1 plus e to the power minus beta epsilon 1 minus mu. Okay. When I look on Z2, the same thing happens. So Z2 is going to be a sum over N2 goes from 0 to 1 e to the power minus beta N2 epsilon 2 minus mu, okay, which is simply 1 plus e to the power minus beta epsilon 2 minus mu. And Z3 is also going to be 1 plus e to the power minus beta epsilon 3 minus mu. And what we managed to show is that the total partition function of this system, Z, is Z1 multiplied by Z2 multiplied by Z3. Okay? So I have a factorization, but it's factorizable not in terms of particles. And you remember, when I taught you, and we started this language when we were treating canonical ensemble, the only way that I can solve problems in statistical physics when I'm dealing with equilibrium is by the means of factorization. And factorization means that I have to stand on my head and pretend that those are not particles but something else. And I usually call them particles in parentheses, quote unquote. And that basically says that I don't care if they are particles. The only thing that I care that I will manage to factorize my partition function in terms of something. This something are my particles. For this system of particles or fermions, my particles are the energy levels. That's it. And in terms of energy levels, the system is factorizable. I don't care about the number of particles anymore. I can compute it, but I don't really care because what I'm saying is that my math showed me when I'm looking on this level, it doesn't care if this level is occupied or not occupied. You can say, Stas, but wait a minute, the lowest levels are going to be occupied first because they have the lowest energy, right? So the system always, this is what we showed, tries to be in a minimal energy. I will say to you that in a second we will see how it actually happens. This is indeed happens for any system. But when I compute everything, this state does not care about that state, and this state does not care about anything else. Right? So this is the wonders of grand canonical ensemble. I stop caring about number of particles. I can separate and factorize everything in terms of energy. Great. So the moment that we have it, we can compute it. But then I can go forward and complicate it a little bit, right? If we add degeneracy to the system, right? So what is degeneracy? I'm saying, well, this particle have a spin up, right? What happens, or can I add another particle that sits at the same energetic level, all right, but it has a spin down? Okay. So nothing bad happened because this Heisenberg principle that two particles cannot occupy exactly the same state is not broken because they have different spins and they have exactly the same energy, different spins. This is why the degeneracy. How can I use all this formalism that I explained to you right now, again, by using this, that I have two particles at the same energetic level, all right? So how I can going to modify all my formalism? Should I now count from between 0 and 2?
No.
Why not?
אפשר לעשות זה ככה, אבל האנרגיה לא תלויה בזה, אז אפשר לעלות
Great answer. I can basically look at the system and I say, I am treating red particles, or everything that will spin up, and blue particles, everything that is spin down. It's basically as if I'm saying, look, instead of saying I have one single energetic level of epsilon 1, I have energetic level of epsilon 1 for particles with spin up, and I have the same energetic level of epsilon 1 with spin down. Right? Epsilon 1 with spin down equals to epsilon 1 with spin up. So instead of having Z1, I'm saying, well, I have Z1 and I will have Z1 up and I will have also Z1 down, okay, which is going to be equal to 1 plus e to the power minus beta epsilon 1 minus mu. Okay, so I could write here up, and here I would write down, but epsilon up, the value epsilon up and the value epsilon down, they're exactly the same thing. So Z1 up and Z1 up and Z1 down have the same values. So when I'm going over here, when I need to compute everything, the only thing that's going to change due to this degeneracy is that I'm going to raise everything to the power of 2. And that's it. And if I had particles, my fermions, that could have a spin plus 1/2, plus 3/2, minus 1/2, minus 3/2, I would raise everything to the power of 4. So the degeneracy, in general, in this system, enters as a power of the partition function of this specific level. Why is it's that? Because all the values are exactly the same. I'm just considering for each spin that the level is separate. Okay? This is how I solve it. So degeneracy doesn't make things complicated. Does not complicate anything. It just enters as a power in the partition function. Very simple, very, very nice. Okay, but having said all of this, I now can go forward and say, well, remember what we asked you? What are the probabilities? I know that the probability to occupy this state should be much, much greater than the probability to occupy a state with a higher energy. How do I see it? Right? So in order to answer this question, we need to define occupation probability. Probability, okay, of state or energetic level I equals to f of I. So I want to calculate what is the probability of occupying this specific part, this specific level. Right? How do I solve it? Do I care about the other levels? Energetic levels? No. So I'm treating each level as it was one single particle. Right? And I'm using this grand canonical ensemble. So I know what is the probability of being that the particle is actually occupying. Okay, so what is F1? The probability that my particle is occupying level 1. So it's simply 1 over Z1 multiplied by e to the power minus beta epsilon 1 minus mu. Right. That's it. The Boltzmann factor, this is this guy, divided by the partition function. So it's simply e to the power minus beta epsilon 1 minus mu divided by, what is my Z1? Z1 is 1 plus e to the power minus beta epsilon 1 minus mu. Yeah.
אם אתה לא יודע את הספין הזה, אתה לא צריך גם לכתוב את זה שאתה לא יודע את הספין ויש לך שתי אפשרויות האלה?
Exactly. So what is, if I had two probabilities, it's just going to be multiplied by 2. That's it. Right? Now, again, I can make my life easier, and I'm going to say, let's consider that I have no degeneracy. When I have no degeneracy, this is the probability. Yes.
אני עדיין לא מבין, כאילו זה לא להכפיל כמונת, זה כאילו פעמיים שתי אקספוננטים ולבנזל אחד בריבוע?
It depends what you're asking. So the question is, what exactly your question? Right? So if I'm going, and I'm going to say, so let me finish and I will answer. Just a second. So F1, it is, let's take it from to the denominator, everything. It's 1 over e to the power beta epsilon 1 minus mu plus 1. This is my probability to occupy a specific state. Now, you're already trying to ask me, this was the question, if I have spin, what happens? If I have spin, what happens? So, remember, in my perspective, I have different energetic levels. They are the same value, but they are different energetic levels for spins up and for spin down. So when you're asking me what is the probability to occupy level, so do you ask me, is there going to be this situation with spin up, or I will have this situation with spin down, or I'm going to have an additional state that I have two particles spin up and spin down at the same time. So it's going to be multiplication, right? They are independent. This is epsilon 1 with spin up. This is epsilon 1 with spin down. The energetic levels are completely independent. So the probability of doing this and the probability of doing that is exactly independent from each other. So the occupation probability is going to be a multiplication of different probabilities, as it should be, right? So this is also why you have a factor of 2 over here. You can, you can look on each state when I define a state with a specific spin as independent from anything else. State energetic level. If you take all the quantum numbers, you take the energetic level and say, this is a single energetic level, single state that can be either occupied or not occupied. If I have a spin, this is going to be a different level already, right? Doesn't matter that the epsilons are exactly the same. It only means that Z1 with spin up and Z1 with spin down, they are exactly the same. This is math, right? But for your sake, it's just two different levels, okay? Yep.
Why Fi probability is 1 times Z1 more Z total?
Okay, because they are independent. All the energetic levels are independent from each other. So energetic level number 1 does not care about energetic level number 2.
But it's the same particle trouble.
No. Grand canonical ensemble. It's not the same particle. That's the nice point about all this. I describe everything that the total particle, the number of particles can change. Right? I will in a second will say, well, on average, only on average the number of particles is conserved. But in general, when we're treating things with grand canonical ensemble, the number of particles is going to change as a function of time. Right? This is why I managed to do this factorization. Otherwise, it's impossible.
So we are looking at the probability of some level to be occupied and not the probability of...
I don't care about the other levels. So if you want to ask your question, so you're asking the following, right? Let's assume that we don't have degeneracy in spin. It's easier a little bit. So you're asking the following question. I have 3 levels, epsilon 1, epsilon 2, and epsilon 3. And you want to ask the question is, what is the probability of particle, single particle, sitting here? Right? That's your question. And the answer is, this guy is independent of this guy and of that guy, so the probability of this specific state, okay, so being 1, 0, 0, okay, it is F1 multiplied by 1 minus F2 multiplied by 1 minus F3. Because they are independent. And because they are independent, it's just multiplication of probabilities. So when I'm saying F1, I just look on this state. When you're asking me what is the probability in a system of 3 states that only the lowest state is going to be occupied, I need to multiply all of them. Okay? Other questions? Great. So we're going to use this occupation probability a lot. Okay? This is without spin. With spin, we're going to need to consider all the other possibilities. Yeah. How do we compute the average number of particles? Okay. What is the average number of particles?
Minus the epsilon.
Yeah. What is the average number of particles? Okay. Average n. Okay, so one question is, Well, I remember that psi equals to u minus ts minus mu n. So if I remember correctly all the Legendre transforms and their relations to u, I would say that average n is simply minus dou psi to d mu. Okay? This if I remember. But if I don't remember, what do I do? Exactly. I'm going to use my definition. What is my definition? My definition is that n is the total, the average of n1 plus n2 plus n3. What is n1? The number of particles at level 1. What is n2? The number of particles level 2. Number n3, number of particles level 3. I'm using only the definition. Okay? Because, and it's always the same. The average of a sum is the sum of the averages. Okay, so it is n1 average plus n2 average plus n3 average. But what is n1?
We have the probabilities. We can
Exactly, so we can say it is f1 naught multiplied by 0 plus f1 multiplied by 1. What is f1 naught? The probability of not being occupied. We don't care about that at all. So n1 average is simply f1. Okay? And n2 is going to be f2 and n3 is going to be f3. Okay? So in total n is f1 plus f2 plus f3, which equals to, using this formula of occupation probability, it's a sum of probabilities. And it is not the sum over probabilities, it is not equal to 1. Why it's not equal to 1? Because there are different random variables, exactly. Okay. They are not the same variables. I'm not counting over all the possibilities of one single particle. No, no, no. I'm taking 3 different variables and I just add them together. This is why the summation is not going to give me 1. So it is 1 over e to the beta epsilon 1 minus mu plus 1 plus 1 over e to the power beta epsilon minus mu plus 1 epsilon 2 plus 1 over epsilon b beta epsilon 3 minus mu plus 1. So we see that the average number of particles depends on many things. Well, it depends on the specific energies that I have in my system, and it depends on the 2 parameters, beta and mu. Beta is 1 over k Boltzmann T, so it's basically temperature, and mu, it's my chemical potential. So how much it costs, remember, what is mu? dE, or dE to dN, how much it costs me to add or subtract particles from the system. And as I see that, as I change the temperature, the average number of particles is going to be modified. As I change my mu, the average number of particles is going to be modified. This is why we use grand canonical ensembles. The average is going to be dependent on the parameters of the system. The parameters are epsilon 1, epsilon 2, and epsilon 3, fixed, but I can modify the temperature and I can modify the chemical potential. Okay, so they do control the average number of particles. This is very nice that the number average of particles is not constant, is changing as a function of potential or the function as a function of temperature. But in physics or in physical problems, I would like to consider situations where at least on average my number of particles is going to be constant. Okay? So I want to use a system, I want to look on this marker. I would say, yeah, when I increase the temperature or when I decrease the temperature, the number of particles are a little bit modified. So some of the atoms are affected, they run away, some of the atoms are just coming in. But in total, on average, I don't want the average number of particles to be modified. Okay? So in order to do this, I would say I look on this formula Okay? And I ask myself the following question. What I need to modify in order to keep n constant when the temperature is modified. Okay. I invented all of this formalism, not me, somebody else invented all this grand canonical formalism in such a way that the number of particles is going to be constant from one temperature to another. Now I solved everything, which is very, very nice, and I thought to myself, well, it's not enough. Why it's not enough? But because I believe that on average the total number of my particles is constant as a function of temperature, or almost constant as a function of temperature. Right? So I like all this solution. We can calculate whatever we want, right? But I know when I'm going to change beta over here, or the temperature, this guy has to be constant. Okay. So what is the answer if I have two parameters? So this is n, and it's a function of beta and mu. I get this constant as I change beta. What has to be modified?
Mu.
Mu. Okay. So in general, we obtain that mu of t is temperature dependent chemical potential. Now this mu, when it's going to be dependent on chemical potential, has a specific name. Okay. And it's termed the Fermi level. And how it's related to level, we'll explain it in a second. But you see, mu is an energy. Why is it an energy? Well, we can look on this expression over here. We have energy over here. So mu have to have the units of energy. And we already know that. So mu is playing some role of an energy. So if this is an energetic level, and we have epsilon 1, and we have epsilon 2, and we have epsilon 3, mu is also some sort of energetic level, right? And it's not simply some energetic level. It has a name related to Fermi, Enrico Fermi. So it has to be important. And we'll see in a second why mu is important. It's not just, well, how much it costs to bring a particle to the system, to introduce a new particle to the system. It actually defines this occupation probabilities. F1, which is e to the power beta, epsilon minus mu, plus 1. Okay. So this is the probability if I'm looking on any specific state. Here it's 1, but it's general. 1, 2, 3. I'm looking on the state and I'm asking, is there a particle there? What is the probability of this state to be occupied? And mu is the most important, or one of the most important quantities to define this. Okay. So have you heard about sigmoid functions? Great. So this is the fundamental stuff of AI. Sigmoid function. So we plot f1 as a function of epsilon divided by mu, okay? And we are going to plot it for different temperatures. Okay? So basically what I'm saying when I'm taking this epsilon divided by mu out, it's like saying I have 1 over e to the power beta mu, and here I have epsilon divided by mu minus 1. Okay. Now, so, yeah?
To add the one,
Yeah. Thank you. It's very important. Otherwise, it's not sigmoid function. Okay, so what happens when my temperature, or beta mu, You see, first of all, here this is the variable of the x-axis. The total F1 is the y-axis. I have epsilon divided by u, so this is my x. I don't care. It's going to be different values. I have only one parameter now. This parameter is beta mu. Okay, so it is mu divided by k Boltzmann t. Now we're going to have several limits. We can have mu divided by k Boltzmann t, which is large, or mu divided by k Boltzmann t, which is low. Okay. So what will happen when beta mu is very, very, very low? So we're talking about large temperatures. Okay. We're working on large temperatures. Okay. So beta multiplied by mu is large, and I'm looking on this expression over here. Okay. So this is a large prefactor. Here I have something. I don't really know what. Okay, so it's 1 divided by e to some large factor plus 1 is not important. Okay, and epsilon divided by mu only in some specific limits is going to be something. Okay, so it's almost right in this limit when beta multiplied by mu is large, or in the limit of large temperatures. This is almost a uniform function, right? So I'm saying is that it looks like this. It's decaying a little bit, little by little, because it has to decay when epsilon mu becomes very large, but it's very smeared function. Okay? The only thing that I know for sure is that when epsilon divided by mu equals exactly 1, okay, it equals exactly 1, what happens to, what is this occupation equals to? No, 1/2. Okay? Okay, so this happens when beta mu larger than 1. So you see the probability is spread, the occupation probability. It is spread as a function of epsilon divided by mu. It has to be exactly 1/2 for 1, but it's going to be different for different levels. The smaller the epsilon, you see, the smaller the epsilon, the larger the probability. The larger the epsilon, the smaller the probability is to be occupied. Remember what you asked me in the beginning of this class, or at least I try to make you ask me this question, is that we know that for lower energies, okay, there is more probability for the state to be occupied than for the states with the higher energies. But this is exactly what we see over here. Okay? Beforehand, we have a very specific epsilon. This is a very specific state. Now, when we changing epsilon from small to large, we see that this probability of occupation probability, okay, is a decaying function. Okay. So what will happen if I will start to increase my temperature? Or in general, I will start, not increase, I will start to decrease beta multiplied by mu. Okay. So what's going to happen? Large temperatures.
So shouldn't
אז
beta
הבטא mu קטן.
Smaller, sorry. Smaller than that.
אתה יכול להסביר שוב רגע איך הביטוי מתמטית, איך זה הופך את זה לאיזשהו משהו ליניארי יורד?
What? Because it's basically, all of this is almost 1. All of this is almost 1. So it has 1 divided by something that's almost constantly 1 plus 1, so it's 1/2. But in general, when you increase epsilon, exponential is a growing function of epsilon, right? So eventually this guy has to win over the 1 over here. So all the function has to decrease. Okay. Right, so we making beta mu larger and larger. What we start to see that the probabilities of being at lower energies, okay, is going to go up, and the probability of being at larger energies is going to go down. But what will happen exactly when epsilon divided by mu equals 1?
The probability will be half.
Exactly half. Okay? It's not modified at this specific point. When epsilon divided by mu is equals exactly half, this is equals to 0. So we have e to the power 0, which is 1. So it's exactly half. Okay. So what we're having when beta mu grows, we're going to have a function that starts to smear a little bit more. And then it's going to smear a little bit more. Then it's going to smear less and less. And at very large beta mu, so very, very, very small temperatures, okay, you're going to have a step function. So this is the property of the sigmoid function based on the parameter over here. Okay, the larger this parameter, the more this function represents a step function. The smaller the parameter over here, the more smeared it becomes and becomes much more uniform. Okay. And this is why in all the AI technology they love to use those functions, basically because you need to create a boundary between what is accepted and what is not accepted, but it's for another class. In any case, what we see here, this is this large temperatures. The step function is low temperatures. This point, when this step function crosses from exactly 1 to exactly 0, this happens, this happens at T goes to 0. And what we see is that in low temperatures, for energies, or epsilon divided by mu that is smaller than 1, the probability is exactly 1. Okay? So if I'm looking on an energetic state which have an energy that is lower than mu, the probability of it being occupied is 1. Okay? When I'm looking on energy where the energy is larger than mu, the probability of it being occupied is 0. This is why mu have this very nice name by Fermi level, because what it means, for any energy that is below the Fermi level, the probability of this energetic level to be occupied is 0. Okay? And for any energy that's above the Fermi level, I'm sorry, the other way around. The probability of an energetic level with energy lower than the Fermi level to be occupied at very small temperatures is 1. The probability of an energetic level with energies larger than the Fermi level is going to be unoccupied. So if I'm looking on my system of 3 levels, okay. So if I have epsilon 1, and I have epsilon 2, and I have epsilon 3, and I'm telling you the following story. My mu is sitting over here. This is my mu. And the temperature goes to 0. What I'm going to see when the temperatures are low, what I'm going to see at my system. Okay, so is there going to be particles sitting at epsilon 1? Yes, because the F1, the only thing that we care about is either epsilon 1 in this limit, either epsilon 1 is below the Fermi level or above the Fermi level. It's below the Fermi level, so we're going to have a particle that's sitting over here. Okay. I'm looking on epsilon 2. In this limit, it's below the Fermi level, so I'm going to have particles sitting over here. Alright? I'm looking at epsilon 3. Well, there is no, it's above the Fermi level, so there's going to be no particles at all. Okay. So for very low temperatures, in what I've described to you so far, right? No matter what happens to my system, if I have epsilon 1, epsilon 2, and epsilon 3, I lower the temperatures, I know that the number of particles that are going to be inside my system is 2. Alright? But what if I have only one particle? My physical system only have one electron. Hey, we are talking about fermions here. Only have one electron. Where from I'm getting the second one? It's not a good solution, right? So how I'm solving this problem that I am only having one electron. I'm only having one particle. This is the solution. Mu of T is going to be temperature dependent. Okay? So what I'm doing or how I'm solving this problem, I'm saying, no. Mu is not constant. The only thing that I know if I have one particle inside my system, one particle, it is that for T low enough, mu is not going to sit between epsilon 2 and epsilon 3. Where mu is going to sit? Between epsilon 1 and epsilon 2. There I can put my mu, right? And I have one single particle. So I'm putting my Fermi level somewhere, and this somewhere depends on what is the total average number of particles that I have inside my system. The moment I kept this guy constant, and I know that temperature is a parameter that I can change, mu is going to change with this parameter. It's going, as I increase my temperature, is going to go upwards, because then I can occupy also those states, right? I'm going to have this smearing of the step function, basically. Instead of very sharp sigmoid, it's going to be a very smeared function, so I can occupy those states. So as I increase my temperature, this guy goes up. And up, and up, and up, and up. How exactly it goes up? I can compute it from using this constraint, that n is basically constant. Right? So for example, in our case of 3 particles, I know that the average n is what? 1 divided by epsilon minus beta, not minus, beta, epsilon 1 minus mu plus 1, plus 1 divided by epsilon beta, epsilon 2 minus mu divided by plus 1, plus 1 divided by e to the power beta, epsilon 3 minus mu plus 1. Okay? So in order to understand or compute exactly how my Fermi level is moving as a function of temperature, I get this guy constant. Let's assume that I have one single particle inside my system. This is 1. Okay? Beta is my parameter. And then I have to solve this transcendental equation in order to get mu. Good luck with this. But in general, it's doable. If I have a computer, I can plot it and solve it numerically. Okay, so I can obtain what is my Fermi level at low temperatures and at high temperatures. Okay, and how it grows up. Exactly. So if mu is like this, I cannot, at low temperatures, I cannot have a particle sitting over here. Because I have a probability 1 of a particle sitting at the lowest level, because the second level is above mu at this limit of low temperatures, there's no particles. He was never there. He was never there. It was an illusion. Right? It was an illusion. Because what I changed, what I modified, you're completely right. What I modified, I said that my Fermi level is not here, it is there. So I completely changed my system. It's not a small thing to change the Fermi level of a system. So what I plotted before, okay, when the Fermi level was over here, and the moment I shifted my Fermi level downwards, the situation is forbidden by the laws of physics. I couldn't put this particle over here. It couldn't be there. No. Heisenberg exclusion principle forbids from this guy to sit over here. And I'm using this. I'm using this physical constraints because those are physical constraints. Heisenberg exclusion principle and this whatever we got from the Fermi level to use and say, if I have only one single particle in my system, it's going to define how mu is shifted, right? And not the other way around. Okay? So I solved it saying, well, mu is something, can be whatever I want. And then I turned everything upside down and said, no, no, no. N is my constraint parameter, and then mu has to be defined by this specific N. Yes?
I didn't understand what you did in the last step. We said this average N is for 3 particles.
No, it's for 3 states. It's for 3 states.
3 states.
3 states. Remember what I factorized? States.
Yes.
Okay, this is important. I factorized states, and I went to every state and asked what is the average number of particles at this state. Right? Other questions? Yes.
אז בעצם אם רמת תפילונית כביכול הייתה נמצאת בין E2 ל-E3, אז לא הייתי יכולה להבחין בין E2 ל-E1?
No, 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 no. So the question, if the Fermi level was over here, I couldn't say what is epsilon 2, epsilon 1. No, you can't say what is epsilon 1 and what is epsilon 2. There are 2 different energetic states.
אז מה גרם לי להוריד אותם מאיפה שהייתם מקודם?
This was my decision, right? I said, what is my constraint? I said, my constraint is that I have 1 single particle, not 2. Okay? So in principle, if mu is constrained, okay, I know that in this limit of small temperatures, I have to have 2 particles. Because the probability of this guy to be occupied is 1, the probability of this guy to be occupied is also 1. I have to have 2 particles. There is no way out of it. But if I turn the other everything around and say, no, what is constrained is the number of particles. Okay? I'm saying to you that there is only 1 single particle inside the system. This means that mu cannot be above epsilon 2, because if it's above epsilon 2 is going to be occupied. Right? So you can distinguish between states. It's the only question of what you are taking as the important and conserved quantity. Is it n or is it mu? We developed everything as mu was the important parameter. Okay? But now we say, well, we have the math, and nobody, okay, even the head of our department can force us to say mu is more important than n. Okay? Yes.
רגע, אני לא כל כך מבין עדיין למה אם זה היה יותר גבוה מאפסילון 2, אז הייתי צריך בעצם בהכרח שיהיה לי חלקיק באפסילון 2.
So the question is, what is the probability if mu is over here for this guy to be occupied? It's 1. So there is a particle sitting over here.
למה? יש לך את אפסילון 1?
No. They are independent. Whatever happens at epsilon 2 is not affecting whatever happens on epsilon 1. Independent states. Right? This is the state of mind. I forgot about the particles are not important. I factorized over energies, not particles, energies. So remember, those are independent.
זאת אומרת שזה מצב לא אפשרי.
No. Yes.
But it only tells us that mu is supposed to be somewhere between epsilon 1
That's
and
right.
2.
Absolutely right. Because, well, I cannot exactly, even for this simple example of 3 states, I cannot solve this equation. This is why I'm wandering around and saying if it's over there, if it's over here. You can solve it, we can solve it on a computer, right? And see how it goes. And it will exactly describe to you what I'm saying with precise numbers, right?
But it will give an exact number of
Yes,
mu?
yes. Given epsilon 1 and epsilon 2 and epsilon 3, you can solve this. Look, you have the only unknown is mu over here. And this equation is definitely solvable numerically.
The only constraint is that mu is supposed to be, like, the epsilon 1 must be lower than mu.
The other way around, I constrain my energies. This was my system. Okay, so remember how I started all this formula. Say, I have a specific energies in my system, then I have parameters. My parameters were this Lagrange multipliers, where they provided to me beta and mu. Okay, beta is 1 over k Boltzmann T, mu was something. But this is something that I obtained when I derived my Fulmerism. The thing that was constant all the time were the energies. I do not modify my system. I modify parameters, I modify average quantities like the number of particles. I do not modify energies. Yes?
אם אתה מעלה את הטמפרטורה, יכול להתווסף לך חלקיק?
Sure. If my mu is something, but if my mu always satisfies this equation, so on average, on average, there's going to be only one particle in the system. If my mu satisfies this, so the n average has to be 1 all the time.
מה שקובע לך את ה...
Yeah, so mu, I cannot say mu is whatever. The Fermi level is very specific and it's defined by the number of particles and usually the density of particles because we're talking about macroscopical systems, but it depends on the number of particles that I have inside my system. I cannot say mu is whatever. No, it's not whatever, it's very specific because it has to satisfy this equation. Right? This is Fermi level, it's not the Fermi level, whatever. We'll call it now Stas level. It's Fermi level because it depends on something very specific and defines this transition probability, etc., etc. I cannot just make this up. Satisfied? No? All right, so let's go a little bit forward. Whatever else that I want to compute, I'm capable of computing. If I want to compute the average energy, I can. I can do it either by taking some derivative of the grand canonical potential, or I can use the definition of energies. I can compute the average energy over here, I can compute the average energy over there, I can compute the average energy over here, okay? And then I can compute the average energy. Right, so let's do it. Okay, so how, for example, I compute the average energy of my system over here. U, what is U? What is U? It is U1 plus U2 plus U3. This is the total average energy. This is the average energy of state 1. This is the average energy of state 2. This is the average energy of state 3. You can say, well, what is the average energy of state? The state is either epsilon 1. It doesn't have an average energy. But the average here is the average of the system that is composed of only one state. This is U1. So if it's occupied, this is epsilon 1. If it's not occupied, it is 0. Right? So this is simply 1 minus F1 multiplied by 0 plus F1 multiplied by epsilon 1 plus 1 minus F2 multiplied by 0 plus F2 multiplied by epsilon 2 plus 1 minus F3 multiplied by 0 plus F3 multiplied by epsilon. Okay. Great. Any other quantity can be computed in very similar fashion, at least for this simple example of 3 states. Now that we know the 3 states, we can go a little bit further and consider the case of free particles, free fermions. And I consider maybe that I have electrons, okay, in my system. So in general, if I'm looking on my energetic spectrum, and I'm saying, well, the energetic spectrum is already a continuum. Right? So if this is free fermions, so my energy is simply p squared divided by 2m. Everybody are free. It's like ideal gas. It's like ideal gas. This is the stuff that physicists can solve. Some harmonic potential and ideal gas. And some combinations of them. Okay, but so this is my energies. And now they are continuous. All the different energies are continuous. Right? And I know that energy is simply h bar k squared divided by 2m. Okay? So if I have a specific wave vector, my particles are my waves. This is a k vector, and this is the general energy. Okay? I want to compute. I haven't told you yet, but I'm saying that there is some average number of particles inside my system. It wasn't. Never +1. Okay? So, I'm asking what is, so any electron, or there are a lot of fermions, and any electron can have whatever energy it likes. Okay? How I obtain the total partition function.
Integral?
Some sort of an integral, right? But before integral, it's factorizable, right? I have to multiply by all the different k vectors that I have inside my system. Why? Because as previously I can say, look, I can factorize the moment that they are independent. I can always factorize according to what? According to the different energetic states that I have inside my system. Not according to different particles, but according to different energetic states. So I take this epsilon, right, and I divide it by small energetic levels. They're actually continuous, okay? And I say, well, I can calculate the z at this specific level, and I calculate z at this specific level, and I have to calculate z for any specific level, okay? And then I just have to multiply them all. So z is going to be a multiplication over all the different k's, okay, of z of k. Okay? If beforehand I have z1, z2, z3, now I have z of k, which is something very specific. Okay, so what is z of k? What is z of k? It's exactly as in z1. Remember, either the state is occupied or the state is not occupied. So this is nk from 0 to 1 e to the power beta nk epsilon k minus mu. Okay? Which is 1 plus e to the power minus beta epsilon of k minus mu. This is my zk. Okay, so in total, z is a multiplication over k of zk, and I have to add something else here to the problem. What I have to add? 2. Right? Spin, the degeneracy of this specific problem. Okay, I can have spin plus 1/2 or spin minus 1/2. Those are electrons. No, this is what we told you. I look on every k and I say this is k for spins up, and those are k's with electrons with spin down. Okay? Okay, next step. Is just, instead of looking on z, we want to compute psi, right? So what is our grand canonical potential? Minus 1 over beta log of z. So psi equals minus k Boltzmann T, a sum over k. Okay? So here I do not integrate because it's multiplication. This is why in log of a multiplication transform into a summation, sum over k, and here I have log of zk, and here I will have a 2. Okay. Okay. So we have so far psi equals minus 2k Boltzmann T, sum over k, log of 1 plus e to the power minus beta h bar k squared divided by 2m minus mu. I close this and I sum over all the different k's. Now we cannot sum over all the different k's, so what we do? Integral. And in order to perform this integral, so k vector can go from 0 to infinity, right? There are no constraints.
include some density of K?
Great, 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 great. This is the next question. So 1 plus e to the power minus beta h bar k squared 2m minus mu. And here what we have? D of k. dk. All right. What is this d of k? This is density. Debye, right, you're right. The only density we ever developed is debye, so even from this perspective is a right question, answer. So we have d of omega, right? This is what we remember. Okay, it equals to v, if you're looking in three-dimensional space, divided by 2 pi squared, k squared, dk to d omega. Right? This was the answer.
סטס, אבל זה מגיע מגלים עומדים, מה הקשר? זה גל חופשי.
No, it's electrons in a box.
נכון.
Right? Otherwise they will run around somewhere and I'm not going to have anything, any effects. Right? So eventually all the electrons, all my fermions have to be somewhere. Otherwise, it's exactly what happens to the electron gas. They run away. Right? Even here, so I have to constrain them that they are going to sit in a very specific box. Right? So it's like what happens to electrons in material. That's the general question.
So why didn't we say they are continuous? If there's only specific energies that an electron can be on.
Yes, and what are they?
Pi k, 10k.
So you're saying the following question, and this is good. You're saying is, well, if I'm looking on the different energies, I will have some discrete spectrum over here, right? And only after a while, it's going to be very, 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 very continuous. Okay? In a second, we're going to see that, well, we neglect this behavior. We neglect it, but it's actually something that is we can do, and I will explain it to you in 10 minutes why. Right? So you're completely right. There are a discrete spectrum, okay? When we are going to very, very low energies. It's not going to be continuous spectrum. Only for higher enough energies, because we're looking on particles in the box, you're going to see something that looks like continuum, right? But we neglect this behavior. Right? I will show you why in a second.
Why did you take, למה לקחת את הספקטרום from 0 עד אינסוף?
This is what I answered. Because because otherwise I cannot solve the integral. This is the main reason. And also because the k or the energies start from 0. They have to start from 0. Oh, yep. No, this is the volume. No, this is, what was v? This was v squared? No. No, okay, so my mistake, sorry. Alright, so let's solve it, right? What's happening over here? So what is this integral over here? So we have psi minus 2k Boltzmann t, an integral from 0 to infinity, a log of 1 plus, oh, what I missed, you're not following, and this is why I know why you're not following. This should be plus. Right? Because this guy is 1 over z. Or not?
What?
Now? Too late for me. You're following, I'm not following myself. Sorry. Okay, so it's a log of e to the power minus beta h bar squared k squared minus divided by 2m minus mu. Okay? Multiplied by what we have here, v divided by 2 pi squared. Okay. Now, what is k squared? Let's write it over here. H bar k squared divided by 2m equals to epsilon. Okay.
רוצים אבל להישאר ב-K.
Yeah, yes. Or we want to move to what variables? So we have dk, right? Or generally d omega. Because we want to express k in terms of omega and k in terms of omega. This is what we did for d pi. Now, instead of doing this, I was going to say this is d of epsilon. Okay? This was d omega, d omega. So I'm going to say this is d omega, d omega, d epsilon, d epsilon, d omega, d omega. Remember, first here, how we transform densities or how we transform probabilities when we're changing the variables. Right?
The omega the epsilon, the epsilon.
Wait. So this is going to cancel each other. So we have omega as our parameter. Okay. Now instead of omega, this is the number. Now what I'm changing is instead of epsilon, instead of omega, I'm changing epsilon. So the total number here is the density, exactly the same, multiplied by this guy, the epsilon by the omega, multiplied by the omega. Okay. This guy cancels out. And we're getting that d epsilon equals to the omega. And this is what we are going to supply instead of this integral, right? So here we're going to have, instead of h bar k squared divided by 2m, we're going to have epsilon. Okay. Now we need to supply k squared. What is k squared?
2m epsilon divided by h.
2m epsilon divided by h bar. And we have dk to d omega, which is going to do what? What we assume that, what is k? So we need some dispersion relation, right? Let's write it over here. K omega divide, what is the usual dispersion relation that we use?
K. Also K.
Omega equals kc, or k equals omega divided by c, dk to d omega equals to 1 over c. We are fine with that? Not? I might lost something? So we have 1 over c, okay? And we have d epsilon. Looks good? No? Why not? Because I don't want to use this guy over here, right? I want to transform everything in terms of epsilon, right? So if I transform everything in terms of epsilon, what stands over here? This is dk to the omega, right? So instead of using, I don't want to look on dk of the omega. I want to look on dk over d epsilon multiplied by d epsilon by d omega, right? dk to d omega equals to this guy. dk by d epsilon, I'm going to have to take a derivative of this quantity over here. Okay, so k equals to 2m epsilon divided by h bar squared. So dk to d epsilon equals to a square root of 2m divided by h bar multiplied by 1/2 multiplied by epsilon.
It's h bar squared.
H bar squared. Okay. And here I have epsilon 1/2. Okay.
מינוס חלקי, לא? 1 חלקי 3.
Minus. So instead of having this guy, I'm having that is 1 over 2 square root of 2m divided by h bar squared epsilon to the minus 1/2 d epsilon. This is exactly the formula. So I have epsilon, epsilon to the minus 1/2. I have a lot of halves that I have to cancel out. Okay, so let's write down the final form. Psi equals 2. I have, let's take everything that is not related to the epsilon out. So I have 2k Boltzmann T, V, 2m epsilon, 2m, minus 2k Boltzmann T. I have V, I have 2m, I have a square root of 2m. Okay, so what I have downwards, I have 2 pi squared h bar 2 to the third power. Okay, and I have another 2. And I have another 2. And inside I have an integral from 0 to infinity, a log of 1 plus e to the minus beta epsilon minus mu, epsilon to 1/2 d epsilon. Now it looks okay, I think. Have I lost something? I don't think so. Okay, so we have here 2 and 2, and 2 and 2. Right. Anything else that I forgot? And I can do this guy, and I can do it as n to the 3/2, and I have a square root of 2. So this is my grand canonical potential. The moment I have it, I can take derivatives of this grand canonical potential and obtain any result that I want.
That's the long illustrated.
Where?
By epsilon.
No, I had an epsilon over here. No, it's fine. Perfectly fine. No buts. Great. So if I want now to go and compute the different stuff that I have inside, for example, what is the critical value? We already know that defines everything, how those electrons behave inside this box. I can compute the n, okay, which is equals to minus del psi to the mu, okay, and then out of this, at least at the limit of the small temperatures, I can compute the Fermi level, because everything is defined here by the Fermi level, at least at low temperatures. At higher temperatures, everything is going to be smeared out, right? But at low temperatures, I know something about the system. I know that it's occupied up to the Fermi level, and it's unoccupied above the Fermi level. And how many exactly number of it's going to be occupied is going to depend on this number n. Okay. So, two things. We can either take this and start making derivatives, or we can say it's easier, right? It's easier if you don't remember this formula. If you're not, do not like to take those long derivatives, or you don't remember it. And I never do. Okay, unless you really love this Legendre transformations. You can say, well, the different n, okay, the average n, is the sum over all the k's, and I'm going to have fk, right, probability to be of this guy to be occupied, multiplied by 1, right? So I'm going again to transform it. Okay, the summation, I can say, well, it's a sum over fk. What is fk? It is 1 divided by e to the power beta epsilon minus mu plus 1, okay? An infinite from 0 to infinity. And here I will going to include the density that we just calculated, d epsilon. So this is the average energy. Yes?
Isn't the sum over all fk supposed to be 1?
No, because there are different variables. Remember? Different states. The probability of the state to be occupied plus the probability of the state to be not occupied is 1. But those are different states, different energies, and they are independent. Remember the 3 states? The different energies were independent. The same goes over here. Okay? Okay, so when we do this, we obtain that the average n, it is v divided by 2 pi squared 2m h bar squared 3/2, an integral from 0 to infinity e to 1/2 divided by e to the beta epsilon minus mu plus 1 d epsilon. Okay? Very nice integral. Okay, so this is n. You want to compute it. If you want to compute, or if I force you to compute it, you never want anything. But if I force you to compute it, right, this is how we compute n. If I force you to compute the average energy, how it's going to look? It's again an integral from 0 to infinity, right? We can say, well, we're averaging over different values of energy, which is epsilon, right? We have some distribution of the energy levels. This is d epsilon. And we put inside, again, this prefactor, which also has the name. Has a name which is called a Fermi distribution. 1 over e to the power beta epsilon minus mu plus 1. Why it's here? It's here because everything starts with the occupation probabilities. And we assume that all the different levels are independent. So this is why this f of k always turns around. Here, and always here. So if you want to remember this something when we're talking about fermions, it always, you sum over all the different energies. There's some distribution of energies, of course, and you have to modify everything by this Fermi distribution. Why it's there? Not because he thought and just put it inside out of the blue. It comes from the summation over all the different energetic states, and all the different energetic states in the grand canonical ensemble are independent. Okay? This is why we have this guy over here. So it's very simple to compute average values, okay, for the grand canonical representation, because we only have to know what is the definition of the value that we want to compute, okay, and we have to plug inside this Fermi distribution. Okay. No matter what you want to compute, if it's fermions, put the Fermi inside, you do this integral, and you're done. All right, so let's take this guy, and we still have like 10 minutes, and let's try to see what is the solution of this integral for t goes to 0. Why it's an easy limit, and why is exactly this limit I want to compute.
Because then we can neglect the 1.
Then we can neglect the 1. This one?
Yes.
Not exactly. Oh. You will see in a second. Okay. What happens when t goes to 0? Sorry? Why? Why there are only two states? No. There is, we have shown something different. So in the limit of low temperatures, what do we know that happens? Yes. It's a step function. So what is a step function? This guy is a step function, right? 1 divided by this guy is a step function. Okay? So all of this integral, this is why it's easy. In the limit of small temperatures, in the t limit, okay, t goes to 0 limit, the average n is simply v divided by 2 pi squared 2m h bar squared, an integral whatever, this Fermi distribution is a step function. That's what we've seen. It's a step function up to mu. So it's an integral from 0 to mu. So the step function is 1 divided by e to the power beta epsilon minus mu plus 1. Okay? Everything else stays the same. This is why I don't care if it's plus 1 or minus 1. It's greater. I'm just saying all of this is 1 multiplied by epsilon 1/2 d epsilon. Okay. So we know to solve this integral, what's the solution of this integral? N equals to v by 2 pi squared 2m h bar 3 to the halves, and we have 1 or 2/3, 3 to halves. What do we have?
2/3
Mu
3 halves.
to what value? 3/2. Okay. So first of all, this is nice. Why? Because see this value. So it is, we have n, the average number of particles, divided by v. So what it is, it's a density, right? Multiplied by 2 pi squared divided by 2m h bar squared to the 3/2. We have 2, 2, 2. We have 3 over here. Okay. All of this to 2/3 equals mu. This is the Fermi level when the temperature is exactly 0. Exactly 0. This is the Fermi level. So what do we know? We know that in the system we have a box of volume V. This is the volume. And we have a lot of electrons inside this volume. And all those different electrons are completely free. Okay, this was our assumption. They do not interact. They even don't feel each other. Right? In what sense? We forgot about Coulomb forces. But the only thing that we do assume that the Heisenberg exclusion principle, Pauli exclusion principle, is working. Okay? So they cannot sit exactly in the same state. That's the only thing that we assume. We haven't forgotten that they are electrons, but we forgot that they somehow interact. Okay? Now, moreover, we know what this quantity n over v, okay? We know what this quantity n over v for metals. It's around, so average number of particles divided by v, it's around 10 to the power 22 or 10 to the power 23. This is the number of electrons in a metal. Okay? So, given that, we know what is the Fermi level, and it's for the lowest temperature. So for any higher temperature, the Fermi level is going to do what? It's going to rise. Exactly as we showed in the 3-level system. Right? So this, what happens, if this is the energy, this is the 0. Somewhere here is the Fermi level, mu. Okay? In our model, we know that all the states below mu are occupied. Okay? And there are no electrons above mu. This mu, when we take the average number of regular metal, where we have around 10 to 22 or 10 to 23 electrons. So for this kind of value, if we take mu divided by K Boltzmann, okay, we obtain 10 to the 5 Kelvin. So the energy up to which value all the states are filled, and above this value all the states are empty, is what? Is as if we have heated the system to the 10,000 kelvins. So it's extremely hot. But it's not, right? Because we have taken this limit of t goes to 0. So what I'm trying to tell you here, okay, I'm saying the mu is as if this energy is as if the system was at extremely high temperature, but the room temperature is very low. Okay. So what it means? It means that this energy, the energy mu, and here are sitting all the electrons up to energy equals 0. Okay. This energy is extremely high with respect to a normal temperature, a normal temperature in a room temperature, or to the 0 temperature. This is an extremely high energy. All the different electrons are filling all these states up to this mu. There are absolutely no electrons above it. The system sitting in its lowest energy. This is what we studied so far. Okay. And this is why actually I can neglect the different interactions between the particles. Okay. Why it's so? Okay. So remember, I said to you, well, there are electrons inside the system, and all the different electrons are not interacting. Only the Pauli exclusion principle is in work. Okay. Now I'm saying, well, I did that, and I obtained that the Fermi level is very high. So I basically filled up all the possible levels, energetic levels, up to an extremely high value. Okay. Now, what is this energy here? Epsilon. This is the kinetic energy of the different electrons, right? It's the kinetic energy because epsilon is h bar k squared divided by 2m, which is actually p squared divided by 2m. So this is kinetic energy. What are the electrons that are going to participate in the metal? So all the electrons that are going to sit here, those states are going to be occupied all the time. The only electrons that are participating in the game of exchanging, so one electron gets kicked out, the other electron gets in. So what will happen if I raise my temperature? Okay? What will happen if I raise my temperature a little bit? So I will start to see a smear of this step function. Okay? Some particles are going to jump from those states to higher states. Right? So if I plot the occupation function, okay, this is epsilon divided by mu. This is the occupation probability. This is 1. So at t equals 0, I know that all the states below mu, so epsilon divided by mu is less than 1, are exactly occupied. This is 1. And all the states above mu are exactly empty. But I raise my temperature a little bit. Mu shifts a little bit. What happens to the occupation probability? It's going to be smeared, right? So it's going to be something like this. Okay. So we have states in the vicinity of 1. Okay, states in the vicinity of 1, in vicinity of mu, because this transition from 1 to 0 is not a sharp transition. Alright? It's not a sharp transition. It's a smear transition. So in the vicinity of mu, there are going to be states that are sometimes occupied above mu, and there are going to be states that are below mu that are sometimes unoccupied. Okay? What it means that we will have electrons that are getting kicked out by thermal interactions or whatever from those states going up, okay, and sometimes they are going to go down. So I have some exchange of electrons from those states to these states, and vice versa. This is why this is a little bit lower than 1, and this is why this part is a little bit higher than 0. Okay? So I'm going to have exchange of electrons between the different levels, But it only happens, you see where it only happens? It only happens in the vicinity of where epsilon equals mu. So only around the Fermi level, I'm going to have some electrons that are participating in a game of conductance or resistivity or what the different functions of the metal that I will have. It will only happen around, at least in this my model, it will only happen around the Fermi level. Right? This is why it's important. I increase the temperature, this guy smears out, but it smears out only around the Fermi level. This is why the Fermi level is important. And here comes an extremely interesting point. This is why I had to compute this mu, and I said to you that this is extremely high energy. Mu is extremely high. Okay? So what are the electrons, or what are the kinetic energies of the electrons that are going to get up or going to get down? What are their kinetic energies? They are on the order of mu, right? They are sitting over here. Only the electron that is around the zero energy is never going to be kicked out and get up. Why? Because the probability of occupation of very low energy is very, very, very close to 1. Okay? So all the electrons are coming only from this region. And in this region, their energies are comparable to mu. Not energies, kinetic energies. Okay? So I have particles that are participating in some game, right? But their energies are very, very high. Their kinetic energies are extremely high. Okay? On the order as if they were very hot, at temperature of 10 to the 5. So do I care if they have interaction or not? I do care about particles that have very low energies if they do interact. This is for sure. But do I care about interacting particles here? The answer is not really. Okay? This is why this approximation that I took, I said, forget about the interactions. This is why it's a very good approximation, because the Fermi level is extremely high in systems where n divided by v, this is mu, you see? Where n divided by v is large. Where I have a lot of electrons in my system, this is what happens is they start to fill up the lowest energies. They are sitting on top of each other, as if they were particles. Right? And only some particles that are sitting there above the roof, they are doing something, but their energies is extremely high, so I don't care if they have additional potential energy. It's not important anymore. Okay? So this is why this gaseous state is actually a very good approximation to what happens in metal. Okay? We can compute the energies, we can compute everything, and it happens only due to this fact that Pauli exclusion principle prevents particles go to lower energies, because all the lower states are already occupied. They piling one on top of each other, and only the particles that are sitting up there doing something, but their energies is very high, so we really don't care. Okay? So this is a nice explanation of a very simple physical fact. The moment that we have Pauli exclusion principle, it's so strong that additional interactions are not important if we have a lot of particles, because they have to pile up on top of each other. We have a lot of them. They will pile up to an extremely high value, and only those guys that are up there, because those guys are restricted, they cannot move, only the guys that are up there moving, but they have so large kinetic energy that we don't care about any additional effects. All right? So this is very nice. That's what happens to fermions. So on the next lecture, we will see that for bosons, it's completely the opposite. What happens for bosons is that instead of piling up on top of each other, and this is what leads to irregular conductance and the physical laws in metals, bosons, they will go, there is no Pauli exclusion principle. So instead of piling up in this direction, they will pile up on a very specific single energetic level. And this leads to a fantastic effect known as Bose-Einstein condensation. And this leads to superfluidity and superconductivity, that all the system is living in one single state. Here, the system is living up there. Bosons living in one specific quantum state. See you next week. Oh, by the way, I still owe you 1 hour. You prefer it this week or next week?
Next week.
Next week. Okay.
ביום שלישי יש שיעור.
אני יודע. לא, אני החסרתי שיעור אחד, ושתיים התבטלו בגלל מבחנים, לא התבטלו בגלל מבחנים. אז אני חייב לכם משהו.
אתה יש לי שאלה על ההגבלה של K מ-0 לאינסוף.
כן.
K הרי זה כמו 1 חלקי למה.
כן.
יש לו הגבלה גם מ-0 וגם לאינסוף, כי הקופסה היא סופית.
אבל נניח שאני יכול, אתה צודק, זה גם את השאלה. כלומר, האנרגיות הנמוכות הן לא רציפות. יש איזושהי מגבלה, אתה זוכר שאמרתי שאני אענה על זה ולא הספקתי? שיש לי 0, ואחר כך עוד 1, ואחר כך עוד 1, ורק אחר כך זה מתחיל להיות רציף. נכון?
למה זה לא? אין לי בעיה של רציפות, יש לי בעיה של
קאט-אוף תחתון, אבל הוא קטן. אתה מבין, האינטגרל שלי, בגלל שהקאט-אוף העליון הוא מיו והוא ענק, הקופסת קאט-אוף התחתון הזה לא משפיע לי בכלל. אתה צודק, הוא שם, אבל הוא זניח לחלוטין בגלל שהדבר הזה גדול. ברגע שזה קטן, יש לי חלקיק אחד במערכת, אוקיי? או שני אלקטרונים, או משהו בסגנון כזה, ואני מקבל אלקטרונים תמוכות, הכל משתנה. אני חייב לקחת אינטראקציה בחשבון. זה בגבול טרמודינמי של מערכת מאוד גדולה, שאין מאוד גדול. ברגע שאין לך את זה, אז אתה חייב להכניס גם אינטראקציות, כי אז אתה חייב להתייחס מה קורה באנרגיות נמוכות, כמו שאתה אמרת, אני צריך לקחת את זה בחשבון.
רגע, אבל יש גם הגבלה מהצד השני, שלמדה לא יכולה להיות גם קטנה מדי.
זה בסדר.
זה כמעט אינסוף.
כן, זה ממש ממש גדול. תודה. כן. כן, בדיוק. אבל זה הכל נובע מהמיו הזה. אתה מבין, אם היה לי מיו יותר גבוה, משום מה, ככה בניתי את המערכת, זה לא יכול להיות גם פה, מיו זה איזושהי רמה אנרגטית, היא לא חלק קוונטית.
אם היה לי שתי חלקיקים, אז המיו היה...
אז הוא היה מאלץ את המיו במערכת הזאת, הוא היה מאלץ את המיו לעלות מעל הרמה השנייה. כן.
למה אחרי זה דיברנו על חלקיקים?
מאוד גדולה, כן. ברגע שזה חופשיים ואני הייתי צריך שזה יהיה גדול.
קצת בדק.
כן.
לשאול כאילו, הניתוח שעשינו עם הצפיפות.
זה שם.
זה לא just
כן.
הניתוח שעשינו עם הצפיפות.
כן.
א', למה בכלל היה לנו מותר להשתמש בצפיפות של בבית?
כי אני מניח שזה חלקיקים גליים. כן.
אלקטרונים.
אתה צודק, אבל האלקטרונים, כשאני רושם את האנרגיה שלהם, הם מתנהגים כמו חלקיקים בדיוק. אני רק אומר, הם מוגבלים פה, בפנים, אוקיי? לאנרגיות נמוכות, אז זה בעצם גלים עומדים, זה מה שאני אמרתי. אז לאנרגיות נמוכות, אני הייתי אמור לקחת את האנרגיות הנורא ספציפיות של הגלים העומדים. ככל שאני עולה קצת יותר באנרגיות, אז הדבר הזה, של הפתרון של גל בקופסה, הוא הופך להיות כמעט רציף. הוא הולך כמעט כמו חלקיק חופשי עם הקי בריבוע.
אני אספיק לעבור על זה, אני אספיק לשבת.
נכון? תחשוב רגע, יש לי פה משהו שהוא מאוד מאוד תלוי במה שאתה אומר, כן, הספקטרום העבדי, אבל באיזשהו שלב הוא מתחיל להיות רציף, נכון? תפתור, תראה.
זה מתחיל להיות ה-D של משהו שהוא משהו בריבוע.
נכון. תסתכל, לא, אתה צודק, כלומר, היה לי חתיכה של ספקטרום שהוא לא הולך כמו גלים.
איזה חתיכה של ספקטרום זה?
חתיכה תחתונה.
לא, כאילו במודל דיבאי או במערכת שלנו?
במערכת שלנו. מערכת שלנו, עזוב דיבאי. דיבאי הוא אומר מבחינתו, הכל רציף, הכל גלים וכן הלאה. אני אומר, אז פה הטענה היא כזאת. החתיכה התחתונה של הספקטרום, היא משהו זה הוא פונקציה של מה בדיוק אביא, ואיך אתה בדיוק פותר את הכל וכן הלאה, אבל הוא משהו. עכשיו באיזשהו שלב מתחילות לך רמות כמעט רצף, ממש רצף, אוקיי? והוא ממשיך עד למעלה. בגלל שהמיו, תשים לב, המיו יצא לך ענק שם.
אבל לא תמיד יצא לך, לא?
אתה צודק, כשהאין חלקי D לא גדול, אז מיו לא גדול ואני לא.
אז יש לנו בעיה בכל הפתרון.
יש, אתה יודע, ה-strongly interacting electrons זה תחום ענק ומאוד גדול במכניקה, לא מכניקה, בקונדנס מאטר, אוקיי? רוב האנשים איכשהו מסתובבים שם בתחום הזה. עכשיו, הדבר הזה נעשה לפני 80 שנה, ומאז עושים דברים כשיש אינטראקציה חזקה. כשהכל חם, אז הכל גז והכל פשוט. זה בדיוק מה שמתרחש. כשיש לך לא הרבה חלקיקים, ויש לך עוד כל מיני דברים, אז כל האפקטים שהם יושבים יותר למטה פה, הם הופכים להיות נורא חשובים. אבל כשיש לך כל כך באיזשהו גבול שם, והאלקטרונים חייבים לשבת אחד על השני. זה בעצם הפיזיקה. הם חייבים לשבת אחד על גבי השני, וכיוון שיש לך הרבה, אז הושבת אותם עד למעלה, ואז אתה לא מעניין אותך איזושהי חתיכה סופית קטנה פה. יש לך המון שם עוד יושבים שהם מתגברים על כולם.
ועוד מודל דבאי הוא הניח ספקטרום בדיד, לא? כי אחרת כאילו...
הוא דחף משוואות של איינשטיין פנימה, כשלאיינשטיין הייתה איזושהי נוסחה להתחלקות של האנרגיות. זה הכל.
מצד אחד המודל דבאי הוא הניח ספקטרום בדיד, ובאמת זה שאנחנו ספקטרום בדיד, אז אפשר לנו להשתמש בגוף שחור, ולא לקבל את ה... איך זה נקרא?
התבדרות.
ההתבדרות שם, ומצד שני יש לנו די של אומגה רציף.
נכון.
אז זהו, זה
מה שאני אומר, אתה יודע מה, זה פותח לפני שקוונטים היו קיימים, אוקיי? וזה היה ניחוש שאיינשטיין לקח מפלנק, והוא הכניס, כי זה עבד לגוף שחור, אז הוא הכניס את זה פנימה, ודבאי אמר, רגע, לא, אין פה חלקיקים כאלה גלים. אם כבר מדברים על גלים, אז צריך לדבר על גלים עד הסוף, ואז נכניס את הרצף ואת התנודות וכן הלאה.
אבל מודל דבאי זה לא גלים עומדים?
זה גלים עומדים, נכון.
אז למה יש לנו ספקטרום רציף של גלים עומדים?
כי זה
פשוט מניחים ש-K מספיק קטן?
כן. כי דבאי פשוט אומר, יש לי איזשהו K, אני לא יודע לגבי קוונטים, יש לי איזושהי נוסחה שאיינשטיין הכניס לי פחות או יותר, אבל יש לי איזשהו K. ואני מניח, כן, שה-K הוא הולך ככה, שה-D אומגה שלי תלך ככה. כלומר, K כפונקציה של אומגה שווה או DK ל-D אומגה שווה ל-1 חלקי C. וזהו. הוא מכניס יחס דיספרסיה פנימה, אוקיי? ואז הוא אומר, יש לי עוד כל מיני דברים אחרים, זה כל מה שמעניין אותי. זה ניחוש מאוד מוצלח וחשיבה פיזיקלית. אתה מנסה לבנות את זה מהקוונטים, הוא אומר, יש לי פה חלקים שלא ממש ברורים לי, אבל גלים אני מבין, ובגלים, כן, הגלים מתחילים מאפס ועולים כלפי מעלה.
אבל למה ריבועית?
מה?
למה ריבועית?
הריבועית מגיעה מ-D אומגה. היה שם K בריבוע. מאיפה הגיע K בריבוע? מהספירה של המצבים. זה מגיע משם. זה לא מגיע ממשהו אחר.
אבל זהו, הספירה של המצבים מניחה קוונטיות.
את זה הוא לא ידע לפתור, זה היה כבר קיים. זה פלנק ניחש, אחר כך איינשטיין ניחש, ואחר כך זה ניחש.
הגיעו לניחוש, אנחנו מנסים להסביר אותנו על ידי...
זה עבד פה, ואחר כך זה עבד שם. זה הביא לאיינשטיין פרס נובל על האפקט הפוטואלקטרי, אז זה סבבה כבר. קוונטים התפתחו הרבה יותר מאוחר. קוונטים התפתחו, אתה יודע, שרודינגר וזה, שנות ה-20, כל הדברים האלה הם עשור לפני. זה בנייה על אפקט פוטואלקטרי.
גם איזשהו המעבר מ-D של אומגה ל-D של אפסילון, לא כל כך הבנתי, כי מכפילים, לוקחים שם איזשהו D אומגה ל-D אפסילון או משהו כזה,
תעבור על זה עוד פעם, אבל תרשום את ה-V, V חלקי פעמיים P בריבוע, יש לך פה K אומגה, DK ל-D אומגה, אוקיי? תרשום את זה כפונקציה של אפסילון, וזה
הכל. כאילו היה לנו D של אומגה שווה ל-DK ל-D אומגה,
זה אומגה, נכון? זה אומגה. D אומגה, אוקיי? זה ה-D אומגה. זה כמות המצבים באומגה ספציפית, נכון? צפיפות כפול רבע.
זה אנחנו יכולים להמיר כפונקציה של
אפסילון וגם את זה.
וגם את זה, אוקיי.
זה כל ההתבלבלות שלי שם.
סתם שאלה לא טובה.
כן.
מוכן לדעת לענות לי מי
גם אני לא יודע. אנחנו נראה. אני לא יודע, אנחנו נדבר על זה לקראת סוף הסמסטר.
סבבה.
בדרך כלל יש מועד ג' רק למקרים מיוחדים, ונדבר לקראת סוף הסמסטר.
קורונה ומספיק...
קורונה, הייתה לך קורונה?
כן.
נדבר לקראת סוף הסמסטר. מקווה שעבר בסדר. כן.
אז קודם כל, כשאנחנו אמרנו פה שאנחנו רוצים שהם יהיה תלוי בטמפרטורה, מה שלפני כן לא היה, זה פשוט בגלל שרצינו עם התלות הזו ש-N יהיה קבוע במקום ש-T יהיה קבוע, שרצינו שמישהו אחר יהיה קבוע, בזמן שזה משתנה.
כן.
רגע, אבל למה רצינו שהטמפרטורה תשתנה בכלל? כשהN יהיה קבוע בטמפרטורה תשתנה. בגלל מה שאמרנו שהוא שווה...
יש קשר, יש פונקציה שמקשרת N, מיו ובטא. וכשאתה אומר שמיו ובטא הם לא קבועים, אז מיו ובטא קבועים, אז מי מגדיר את מי? זאת השאלה. זה בעצם יש לך כזה דבר. N היא פונקציה של מיו ובטא. ואני רוצה להגיד לא או לא. מכאן תמיד אפשר להגיע לכך שמיו הוא פונקציה של, נקרא לזה G טילדה של N ובטא. זה מה שאני עושה.
מה שאתה אומר זה שיש לך בעצם את כל שלושה משתנים, את ה-N, את ה-U ואת ה-בטא, רק שמסדר אותם בקשר לשיעור קודם, שעשינו אז.
כן.
אוקיי, סבבה. בוא נראה, פה, כשאנחנו דיברנו בעצם על טמפרטורות נמוכות וגבוהות, אז בעצם מה שאתה אומר, אני בהתחלה כל הקומה כזו יכול משהו טמפרטורה, נכון?
כן.
ויש לנו בעצם תמיד מקדם פרמי האחד הזה?
מקדם פרמי אחד.
כאילו האחד הזה שכאן, של אפסילון חלקי מיו.
אפסילון חלקי מיו, תמיד אחד.
בחיים לא היה לי קשה ככה.
כן, כי זה תמיד אפסילון חלקי מיו, שהוא שווה 1, אז הפונקציה סיגמואיד הזאת היא הופכת להיות לחצי.
אם לא, וואי.
1 חלקי e בחזקת בטא אפסילון מינוס מיו פלוס 1, כשזה שווה ל-0, אז פה זה שווה ל-2 ופה זה שווה לחצי. זה מעבב.
זה מעבב?
כן. כנראה. יש לכם שיעור עכשיו פה?
כן.
אוקיי, אז אנחנו נעזוז.
כן, אז אולי נשאר אתכם בחוץ מקסימום
מתי אתם מתחילים? ב-6?
כמה זמן חיכית עם זה?
חיכיתי 5 דקות ואז הפסק. ואז חיביתי להם את האור.
5 דקות.
אוקיי, אז תן שיסתכל. אוקיי, אז בעצם אפסילון חלקי M פה זה בעצם...
זה נורא מעצבן, אתה עומד ככה וזה מעבב...
לא, אין סיכוי שאני...
רגע, אז בעצם אפסילון חלקי M פה זה בעצם... כל פעם אפסילון שלי בעצם הוא...
עד שלא הדלקת את האור, לא הבנתי כמה חשוב.
ואפסילון חלקי בטא אני בעצם את הטמפרטורה, נכון?
רגע, בוא נצא.
אין בעיה, לעשות שני תפור.
רגע, הוא אומר לי לא צריך לשמור מקום.
זה גם היה לך. נכון?